it and we'll see how it works. I don't know. Should have recorded it yesterday. I don't know why I didn't. Okay, so remember how last time I think I drew up like a grid on the board, and we talked about like transformations. So like transformations or matrices representing transformations, which are like a new set of grid lines. Something like this, maybe. You guys remember that? Vaguely. So I mentioned that like a matrix is just a transformation, and a transformation is like taking grid lines and like rotating it, stretching it, flipping it, doing something to it so that you have a new set of grids. So we're going to sort of build off of that and talk about this idea of an eigenvector. So an eigenvector is a vector where if you apply this transformation, all it's going to do is like grow the vector or shrink it or flip it or do something to it, but it's never going to rotate it. So under the old grids versus under the new grids, the vector is unchanged, if that makes any sense. It doesn't, well, it's changed, but it's not rotated. It's not like, it's not changing direction. It's only changing amplitude or flipping. Does that make sense? Cool. So that's what an eigenvector is. Now, how many people have done like played a musical instrument in their life? A show of hands. A lot of people. Okay, cool. So one of the neat things about music, and maybe people who have like listened, been to a concert or like been to something, right, will sort of recognize that when someone's playing, say they're playing the piano and they hit notes that are like really good and crisp, it like lasts, it almost lingers, right? And it's kind of full in the air, like you can feel like a sort of fullness to it, right? Whereas if somebody just like jammed their hands on a piano, it's very loud, but it's gone right away, right? Like it doesn't kind of linger and it's not full in the same way. Does that make sense? People sort of feel that? Cool. So that's an eigenvector. Those chords are so we've talked about how vectors could be different things, right? One kind of vector is a sine wave. Different types of sine waves act as vectors, or as a vector space. So music notes are sine waves. When they hit your eardrum, I'm not a biologist, but your eardrum is changing the sound wave into an electrical signal that goes up to your brain, right? It's a transformation from one vector space to another vector space. So it's from the sine waves to electrical signals in your brain. It acts as a linear transformation, which is kind of cool. So those special frequencies that make chords, there's nothing special about them inherently, right? Like there's nothing particular about those chords versus like just jamming some other chords. Like why do we find some chords nice and some chords, not nice? The answer is because the chords that we find nice are eigenvectors. And I think that's really cool. Because so the idea eigenvector, eigen means like special or important or something like that. It's a German word, and it means like special. And so this is like when we think about eigenvectors as like sound waves, that's like an ideal or a special chord that hits our eardrum, and it makes our brain like it for whatever reason. When we're talking about vectors, all we're doing is growing or shrinking or flipping the vector. So it's like a special vector that doesn't change direction. So it doesn't doesn't distort it in any way. It preserves sort of that fullness. And sort of, so going back and forth here between the vector analogy and the music analogy, we've talked about eigenvectors. Maybe you're wondering, what are eigenvalues? Well, eigenvalues are the amount that vector is stretching or shrinking or flipping by. Does that make sense? So it's like the scaling factor. It's the number you're multiplying it by. Does that make sense? Yeah. In the music context, that eigenvalue, well, what do you think that eigenvalue would be in that music chord context? Like, would it be a positive number, negative number, big, small? Any guesses?
Could be anything, I guess. In the context of the music thing, I guess it would go from like 0 to just how loud the sound is.
Sort of. So do you think, first off, maybe I should ask, who thinks it's positive, the eigenvalue in that context? Who thinks it's negative? Who doesn't know? Okay, it's positive, so it is positive. The reason it's positive is because, I mean, sounds can't really be negative. I don't know. That's not really, there's no idea of like negative music. I don't know. It just doesn't really exist, so it is positive. Do you think that it's like bigger than 1 or less than 1? Who thinks bigger than 1? Who thinks less than 1? Why do you think less than 1? Any ideas? Okay. Trying to see if there's a relation. I don't think there is. The answer is it's bigger than 1. And the reason why you would expect the eigenvalue in that context to be bigger than 1 is because the sound waves are amplified, they're growing, they're like stretching in a sense, right? They're getting more full and more, not necessarily loud, but just full and longer lasting, right? So the eigenvalue is going to be bigger than 1. It's going to be a positive big number, right? So it's going to sort of make that sound longer and like fuller. Does that make sense? Cool. Okay, so maybe you're saying like, okay, this is all nice and cool, but like, how do you do math with this? So say that we have a matrix that's acting as a transformation on some vector, and we say that we think that this vector here is an eigenvector, right? So it's that special vector that only grows or shrinks or flips. Well, if it's growing, so I outlined 3 cases, right? Grow, shrink, flip. If it's growing, then that means we're just taking the vector and multiplying it by like a number bigger than 1 so that it'll grow, right? Multiplying by 1 would just mean it stays the same. If we multiply it by something between 0 and 1, then it's going to shrink, right? That's like dividing it by a number. And if we multiply it by a negative, then it's going to flip, right? So we've sort of covered all 3 cases just by multiplying it by some number. And that number is the eigenvalue, right? So when we apply the matrix to that eigenvector, it's the same thing as just multiplying that vector by some number, depending on what that flip, whether it's flipping or growing or shrinking is. Does that make sense? So what that kind of means is that it's usually easiest to find those eigenvalues first, and then based on those to find the eigenvectors. Because eigenvectors, like, well, values are just numbers, right? Vectors have multiple numbers, so they're just generally going to be harder to deal with. So how do we do this? I'm going to manipulate this equation. This is called the eigenvalue problem. It's usually what it's referred to as. What I'm going to do is I'm going to manipulate it. So I'm going to say, well, AV equals lambda IV. Is everyone okay with that? I is just the identity matrix, so I can multiply anything by the identity matrix. It doesn't change it, right? The reason I'm doing that is so that both of these quantities are matrices. Right now, this is a matrix, this is a number. Multiplying it by I just means this is a matrix, this is a matrix, right? I should also note that A has to be square. It must be a square matrix for all this to work. Now what I'll do is I'll bring this lambda IV over to the other side. So I'll get that. I'm just subtracting. And now I can factor out that v on the right, right? And the side does matter because we're dealing with vectors or matrices, right? So order matters. But we can factor that out, right? What if I call this thing here like a tilde, and I call this thing x? What do I have?
System.
I do, right? I have a system ax equals 0, right? And that should sort of be sounding alarm bells in your brain of like equivalence theorem, right? It is, use the equivalence theorem, right? So we remember that this always has at least one solution. This is the homogeneous system, always has at least one solution. It has one if the determinant is non-zero. It has infinitely many if the determinant is 0, right? Of this a tilde thing, which is just this a minus I lambda. So the determinant of a minus I lambda, when that thing is equal to 0, then we have infinitely many solutions. Now, why do we care if we have infinitely many solutions to this? Well, if we only had one solution, that solution would be that v is 0, right? And we generally consider v not to be an eigenvector because, v equals 0 not to be an eigenvector because 0 is always not going to change, right? It's always just going to be 0. So it's kind of like trivial in a sense, like it's like, who cares if 0 is an eigenvector or not, right? We care about the other things, right? The other values. So that's why we're setting the determinant equal to 0, because we want to find things other than the trivial solution to see where's their other solutions. Okay, so what we call this the characteristic polynomial. The idea, it's a polynomial. When you take that determinant, you'll get like a polynomial, so like a maybe a quadratic or a cubic or whatever, where the variable is lambda. So instead of x as variable, you have lambda as variable. Totally depends on the matrix that you're dealing with, but let's go through an example. So say that I want to find the eigenvalues of 0, 1, minus 2, minus 3. 0, 1, minus 2, minus 3. I'll call this A. I want to find the eigenvalues. So eigenvalues are numbers that are associated with that matrix, special numbers associated with that matrix. We find them using this characteristic polynomial by solving it. So maybe a good first step is to say, well, what's this A minus I lambda? All this means is that on the diagonals, you're subtracting lambda. That's it. It's fancy notation. All it means is that across those diagonals, you're just doing minus lambda on each entry. So it's going to be 0 minus lambda, which is just minus lambda, 1, minus 2, and then minus 3 minus lambda. Make sense? Now we find the determinant of that thing. So it's going to be this times this, minus this times this. And I think you'll end up getting lambda. I'm going to cancel out some of the negatives here because we're doing a negative times a negative. Well, maybe I won't. Maybe I'll write it out in full just so you can see it. It's lambda plus 2. And it's plus 2 because we're doing minus what's on the diagonal, right? So minus 2 is plus 2. If I expand this out, I believe I get lambda squared plus 3 lambda plus 2. So it's like a quadratic in terms of lambda, right? From there, I believe we can factor this as lambda plus 2, lambda plus 1. Does that seem right? So our solutions are lambda is minus 2 and lambda is minus 1. Those are your eigenvalues. That's it, right? Not too crazy. Now, we want to find the eigenvalues that go along with those eigenvectors. Now, the way I phrase it is I call them eigenpairs because they come in pairs, eigenvalues and eigenvectors. They come together in pairs. So for every eigenvalue, you have an eigenvector. For every eigenvector, you have an eigenvalue. They're always together in pairs. That means if I want to find the eigenvectors, I have to find the eigenvector that goes along with -1, or -2, sorry, and I have to find the eigenvector that goes along with -1, right? Each of them are going to have an eigenvector. So let's go through it. Let's take a look at lambda is -2, and let's see what happens. So if lambda is -2, then I'm going to sort of look at this equation here, this a minus I lambda times v equals 0. I'm going to try and solve for that v. Well, a minus I lambda is this matrix. If I plug in lambda is -2, then I'm going to get the matrix 2, 1, -2, -1. And every time you do this, a good hint that you're like on the right track is that you're going to notice something a little weird. Like in this case, it's that one row is like a duplicate of another with a minus sign, right? You're always going to see something like that, where it's like a duplicate of a row or like, you know, multiple of a row. You're going to see something funky like that. If you see that, that means you've done it right. Second thing, so V, in this case, I'm just going to break it down into components, V1 and V2. And that's equal to 0, 0. So if I do this multiplication, I'm just going to look at the top row, 2v1 plus v2 equals 0. The bottom row is going to give me minus 2v1 minus v2 equals 0, which is actually just the same thing with a minus sign, right? Just multiply everything by -1, it's the same thing. So I'm only going to really look at one of the equations. If I solve this, I get v2 equals 2v1, sorry, negative 2v1. Maybe what I'll do is I'll say v1, let's set it equal to t, then that means that v2 is minus 2t, right? So I found the eigenvalue in this case. It is, the set of eigenvalues are t and minus 2t, so any possible value of t you could pick, that will give you an eigenvalue, or eigenvector, sorry. Easy one to pick is t is 1. So you get 1 and minus 2, right? Make sense? Any questions about that? No? You can do a similar thing for lambda is -1, and I believe you would get 1 minus 1, and I'll let you sort of verify that. Yeah, it's 1 minus 1. Does that make sense? Cool. Okay, so I think that's it for eigen values and eigenvectors.